Okay, so let's do an example that will illustrate this method, which, as I told you in the beginning, it's really very simple. Okay, so here we have an economist. He's interested to study the spending habits of consumers. The population standard deviation is known. Sometimes, as I told you in the beginning also, it is not very unrealistic to have this while you don't have mu. Okay, so let's assume now that we have it. And he collected the sample of 50 individuals, and he found that their average expenses is 15,000. Okay, so he wants to estimate the mean spending of all the population. Okay, so this is inferential statistics, right? Because to find the average spending of all the population, he collected sample of 50 only from all the population, and from that he found this sample, which we call it a statistic, remember, and we're going to use that statistic to make an inference about the population mean. So that's inferential statistics. Okay, so what do we know here? We know that the population standard deviation, we always denote that by sigma equal to 1000. The sample size is 50, and this plays a very important role in the interval. Okay, we're going to do some problems that will show us the effects of different terms on the interval. Sample mean also, we observe that, so we get from 50 people, we ask them about their spending, we sum it up, divide by 50, and this will be X bar. Okay, so what do you want? In fact, we always have to specify our confidence, right? Because it makes a difference whether I need to be 90% or 95% or 80% confident. Okay, my interval will be different. So the confidence interval, and we learned that this is 1 minus alpha, is 95%. So from that, I can get then alpha, right? Why I need alpha? Because you see in the confidence interval, I need z alpha over 2. Okay, again, remember here I'm using the notation that we learned a long time back, which is ZA. So what's Z alpha over 2? That's a value here such that the area here is alpha over 2. So that's why I need to know what's alpha over 2 so that I can tell what is my Z value, and then I will replace it into that in that term. Okay, so alpha over 2 is obviously 5% divided by 2, right? Because 1 minus alpha is 95. So alpha, okay, is 5%, obviously. So that means that alpha over 2 is 2.5%. Okay, here we go. So now I know that this is 2.5%. So how can I find this value Z? Okay, remember, if this is 2.5% on the right-hand side, that means all that, and why I'm interested into all that, because the Z table show areas corresponding to Z values, and these areas come from the lower tail to that value Z. Okay, so that area, the big area, is what? It's 1 minus 2.5%, so that's 97.5%, right? It's 97.5%. I'm very sorry about this, but this is I'm using a mouse here. Okay. No problem. Let's go ahead. So from the Z table, we look into, by mistake, I got a highlighter instead of the eraser. I'm sorry about this, guys. So this is 97.5%. Okay, let's go back here now. So from the Z table, we find Z 0.025, which is 1.96. What's that? As I showed you in the illustration. So we look for the Z value such that P of Z less or equal than Z is 97.5. Okay, I will repeat it again because look, some students get confused because we have specified that 1 minus alpha is 95, so they think that they have to look for Z value such that P of Z is 95, P of Z less than equal to Z, which is wrong because this is my 95% and this is the Z that I want to find. Okay, this Z has an area below that. It's 95% plus that area, plus that small area here, which is what? Which is equal to alpha over 2. So it's 95 plus the 2.5%, so it's 97.5. Okay, so the Z value is then 1.96. And now I have all the terms because I know X bar, I know Z, I have sigma, and I have the sample size. So I plug everything in place and I get a confidence interval of X bar, which is 15,000 plus or minus 277. So the upper limit I add the 277, and for the lower limit I subtract the 277, and this will be our confidence interval. Okay, so I hope that that was clear. Very simple, but yet you have to be very careful about the value of Z. Okay, so let's interpret our results. As I always tell you guys, whenever you use any statistical tool, finding the results is not enough. The interpretation is very, very important. Okay, so what are we saying? We are saying that that this interval between 14,767 and 15,233 will include the mean of the spending of all the consumers. This is very, very powerful interpretation, right? And notice here that I did not say that that I'm 95% confident that mu is between this and that, right? I'm not saying that because mu is a one value. It does not change. This is the parameter of the population. Okay, it does not change. So I cannot say that the probability that mu is between one value and another value is equal to 95%. I know that many students do not maybe mean that when they make such a probability statement, but just to be careful about that. All right, just always remember that mu is fixed. What we are doing is we are finding an interval, and we are, let's say in this case, 95% confident that this interval include or contain the population mean, and this is what's important. All right, so when we say that we are 95% confident, and what happened to the remaining 5%, we are here admitting that we can be 5% of the times wrong. Okay, and let me go back to that. In the media, they always refer to 95% as 19 out of 20. They like to use that because it's more, it's closer to the people's language, right? It's not statistics anymore, 19 out of 20. So, and this emphasizes, in fact, the long run aspect of a confidence level. So that means when we collect the first sample, second sample, third sample, etc., 19 out of 20 times that we do that, the lower limit and the upper limit will be including the population mean.